This conference will now be recorded.
All right, so welcome everybody to another OCP Tap session. This is the 75th session, and so we have Chris Farrow to present to us about the network and is the clock, I think, resilience at the network layer with ePRTC. So as usual with the format, we'll introduce the speaker, but before we go further, Julian St. James just finished the 9th version of the time card. And Julian, is there any chance you can show it on the camera?
Yeah, let's see how the lighting looks. Okay.
So this is the 9th version. A bunch of improvement came in. We have, can you give us the highlights, Julian?
Yeah, so there's two big changes. One is I added the M2 slot. I don't know if you can see there. So we collaborated with the NVIDIA team to define the pinout for an M2 GNSS receiver as opposed to RCV. So now there's two M2 slots for GNSS receivers at the 2242 form factor, and one of them can support the 3060 form factor. The other large change was that I shrunk the board to make it fit in the half length. So there were some requests that the other card was slightly too long. It wouldn't fit in a normal server that needed a half-length PCIe card. So this one is now a half-length card. And
Wonderful.
There's some other fun changes, but those are the big ones.
And it's available already on GitHub, but you recommend you do some testing before people jump on it, right?
Yeah, so I just got these today, so please wait until I put it into the released category as opposed to the experimental, but should be pretty soon. So thank you.
Wonderful. So now let's go with introducing our speaker. So Chris Farrow is a technical service manager. Chris Farrow holds a first-class honor degree in physics and electronics and has been involved in sync and timing since the early 90s from E1/2.048 megahertz clock recovery cards in early telecom applications, right through to atomic clocks and GNSS timing systems for critical infrastructure. Chris has a solid experience in supporting the deployment, operation, and upgrade of timing systems across a wide range of end use cases. At Chronos, Chris is responsible for all technical services, including synchronization, MasterClass Training, Sync Audit, and network planning consultancy, customer demonstration, and he's also a member of Chronos Product Development Group. Chronos Technology has been delivering and supporting global sync and timing excellence to telecom, energy, finance, broadcast, enterprise, IT, and defense markets for over 35 years. Great. So with no further ado, Chris, the floor is yours.
Okay, thank you. And thank you to the Time Appliance Project for inviting me to speak here today. Moving on from that introduction, it's a pretty good day to be talking about clocks and time sync. I think the summer solstice, the longest day of the year in the Northern Hemisphere. I'm in the UK at the moment. I'm about 200 miles further north than Stonehenge, which is about a 5,000-year-old clock. There's a little bit of debate whether it's a clock or a calendar, but it's built in alignment with where the sun rises this morning on the summer solstice, and also where the sun sets on the 21st of December for the winter solstice. So in terms of this talk, I'm going to talk a little bit about the evolution of reference clocks, specifically for telecom networks. Then take a little detour into some of the security and resilience aspects of the type of clocks that we are relying on at the moment, not just for telecom networks, but for all critical infrastructure. And then get into some of the ITU clock specifications and the clock definitions of how we can build more resilient clocks by connecting them together over the network. This is really superseded by the introduction, I think, just in case you don't know Chronos. Founded in the 80s by Professor Charles Curry, we're now an employee ownership trust There's 35 of us. We're based in the southwest of England. The bottom right-hand picture, the photo on the screen, is actually the HQ where the office and the labs are. We're a manufacturer and a reseller. We contribute into the global telecom timing community by being a member. We're a member of the ITU, Study Group 15, Question 13. We're also actively involved in the two main timing conferences, ITSF in Europe and WSTS in North America. We're involved in the steering groups, and we're also involved in the steering group for the Royal Institute of Navigation in the UK. So, to the title of the talk, the network is the computer, is what it's based on. That the network is the computer is a slogan that first appeared in the 1980s from Sun Microsystems, and I think the concept behind them using this slogan was they thought that the power of the computer was infinitely multiplied by networking them together. Excuse me. So my take on that slogan is the network is the clock. And hopefully by the end of the presentation, we'll look at some architectures where I think by networking clocks, we can infinitely make them more resilient. So that's where the title of the talk comes from. A very quick look at some history. Just listening to that introduction was starting to feel really old. Thinking of when I did first leave university and start working for a major telecoms vendor. But we're going to go back and look even further back into the past and how clocks have developed, particularly for telecom networks. So in the 1920s in the UK in London, there was a person called Ruth Belville who was known as the Greenwich Time Lady. And she offered a service, a time service, time as a service in the 1920s, where she would ride her bicycle to the Royal Observatory in Greenwich, where at the time the reference clock was. She would set her pocket watch to the time, to the clock in Greenwich. Then she would cycle down into London, into the city of London, and take this pocket watch and sell time to the financial institutions, the banks, anybody who wanted to know what the right time was, and they would set their clocks rather than having to do the service themselves. And towards the end of her career doing that, there was some competition and people were besmirching her character and saying that her time was wrong and they had the right time. So analog telephone networks were around at the time, and people started to phone up the telephone operator, the actual human operators, and ask them what the time was rather than rely on this other service. And so the post office, who were in charge of the network then in those days, decided that they were going to create a speaking clock. So they created an electromechanical clock. They recorded the voice of one of the operators, and then you could dial from your rotary dial telephone the numbers that represented TIM, T-I-M, and get through to the speaking clock. So the master clock then was a speaking version, an electromechanical automated version of a human. Move forward now into the much more modern era and to digital networks. So when those telephone networks first started to become digitalized in the 1970s and 80s, they were looking at how to control the slip rates between these digital links between international networks. And the best available commercial clock at the time was a cesium beam tube, which at that time would give you about 1 part in 10 to the 12 frequency accuracy. And they did the sums on an E1 link, the old PDH links, the 2.048 megabit link with a 256-bit buffer. They worked out at the different slip rates. 1 part in 10 to the 11 would give you a slip on that interface once every 70 days, which was deemed as acceptable. And these are scans of actual photocopied documents that I had when I started work, looking back at the standards, and it mentions this 1 part in 10 to the 11, and that is still around today. That's still in G811, the ITU standard for the primary reference clock, is still active today, and it's based on these original specifications. So originally it was a CCITT standard. In 1976, in the Orange Book, the standards were published in those days in books with different color binders. So there was an orange, a yellow, a red, and then a blue book, I think, CCITT ITT standards before they sort of renamed and rebranded themselves as the ITU, and it became an ITU standard then known just by the G number. But that PRC, primary reference clock number, G811, goes all the way back to 1976 and those first digital networks. In the UK, the PSTN, the digital PSTN, was rolled out using a type of telephone exchange known as System X, a digital switch with digital interfaces. And the master clock for that network was in an exchange that was called Baynard House in London. And it had a triplicated 3 cesium beam tubes as part of the telephone exchange. And the whole PSTN network was then synchronized from that. So the network was the clock in those days, in the 1980s, through the PSTN. In the late 1990s, core network technology known as SDH, Synchronous Digital Hierarchy, also known as SONET in North America, the same type of technology, but different bit rates for the North American and the European standards. There's a big clue in the first letter there, S, synchronous. So that this network needed to be synchronized, and it's then when we started to see the PRC specification added to by this SSU, or the bits clock. And in the UK, the network went through an upgrade where the PRC was moved from London Baynard to 2 other geographically different locations, and the network was clocked. The SDH network was clocked from these 2 PRCs. And that's when we first started to see GPS being used as a frequency reference, as a frequency source for these networks. This is a phase error plot from the early 2000s of an ISDN service. So this was into the Chronos office, into the Chronos premises back in the early 2000s. ISDN delivered over an E1 2.048 megabit circuit. The reference was a GPS cesium clock, and the network itself in those days was referenced to GPS and cesium. So overall, it's more or less a flat line. If we can average or integrate for long enough, you can see that we'll get to approximately a flat line. But with these very, very short-term phase transients of 2 microseconds of noise, and that was due to the clock circuits that were in these old PSTN telephone exchanges in the System X. And if we zoom in onto that phase error plot, we can see here there are this sort of sawtooth waveform with peaks and troughs that are spaced apart roughly 30 seconds apart. And this was a really coarse 1-bit control on the oscillator. The E1 data was read into a buffer, and there was a fill level monitor. If the buffer started to get almost full, then the oscillator was switched into fast mode, so it would go faster, so you would clock data out faster and empty the buffer. As the buffer got almost empty, the clock would then switch into slow mode, and you would get this sawtooth behavior of the phase error. So the network being the clock there in the 1990s, early 2000s. But it's interesting because it heralded the use of GPS. So the American GPS system, position, navigation, and time system, declared fully operational in April 1995 on this slide. Recently, Brad Parkinson presented a really interesting talk on the history of GPS and how it's evolved over the 50 years since its inception in the early 1970s. There's a link to the PDF, and you can find the video on YouTube as well. It's the PNT advisory board that he was speaking at. The photograph in the bottom right is of an old Oscilloquartz SSU that in maybe 96 or 97 was actually transplanted into one of those old telephone exchanges as a frequency reference source rather than using those cesium beam tubes. But now, right coming up to the modern day, time underpins absolutely everything in our modern hyper-connected world. It's usually GPS, GNSS, the 4 main constellations, either GPS, GLONASS, Beidou, or Galileo, that is timing something, some part of the modern world. We have this reliance on time stamping in the utility industry, not just the power industry, but the water industry as well. Sampling voltage and current and comparing samples at different locations a voltage and current to work out if there is a fault or any sort of fault condition on high voltage transmission lines. IT and OT networks generally, lots of use of NTP reference clocks and PTP reference clocks now, where GNSS is usually the reference for those financial services. In Europe, in the European financial service industry, there's a MiFID requirement on traceability to UTC, which GPS provides us through the US Naval Office, UTC USNO. Broadcast as well, broadcast industry, synchronization of audio and video streams, not just locally, but from outside broadcast studios to main studios, and also in the broadcast transmitters themselves, actually single frequency networks that use 10 megahertz and 1 PPS reference signals. All of this infrastructure relies on GNSS and telecom all over wireline and wireless telecom networks. The IMT 2020 vision that the ITU published a while ago is what they thought 5G was going to be, the classic triangle diagram that you've probably seen that has at the vertices of the triangle enhanced mobile broadband, massive connectivity, and ultra low latency. All of those things fall away without synchronization. From 4G LTE onwards, and obviously any of the TDD mobile services around the world, they all need phase alignment. And it was 4G LTE Advanced that brought in this requirement for a microsecond or 1.5 microsecond at the edge of the network. That pushed some of the ITU recommendations forward to be able to support those technologies. All sorts of transport industries in terms of asset tracking and also the operation of traffic signaling on the roads and the rail, air and sea, all use GNSS reference clocks with either NTP, PTP clocks to get that into operational networks. So we really have this condition now of those master reference clocks being everywhere. And to paraphrase one of the chief scientists of one of the clock vendors, he said its biggest strength is its biggest weakness. And I think people are complacent with GNSS, particularly GPS. It's always around and it's available everywhere. I know that there have been some well-documented issues and problems and outages with GPS where things have gone wrong. The Space Vehicle 23 issue, and also Galileo as well. Galileo had a week-long outage a few years ago. So apart from that, those isolated incidents aside, the phenomenal uptime of GPS certainly over all those years has led to a certain amount of complacency, I think, and we're only really starting to address those issues now for critical national infrastructure. So in terms of resilience, how easy is it to spoof GPS, GNSS signals? So going back 10 years now, we first tested in our labs this GPS simulator from a company called Coherent Navigation. Now they were a North American Silicon Valley company. I think that they since were acquired by Apple. So I think their technology is now amalgamated into Apple. But we were testing in our labs this particular GPS simulator. Now, the only photographs I have of it are these two photographs. And the reason the top of the box has been removed is they shipped this to us from the States to the UK. And when we unboxed it, the front panel had a huge bend on the side. It was bent. It had obviously been dropped or bounced around by the courier. So we were working with the guys in the States to make sure everything was still okay. So that's the reason for why the lid is removed. But it's basically an RF signal generator that you can control. It has a really nice, or it had a really nice web-based GUI. You could configure all sorts of parameters. The most interesting one for us, obviously, was the time control. And it had a really nice interface. You could do some really subtle attacks on a timing receiver by adding a very small frequency offset, like a part in 10 to the 9. So you add an extra nanosecond every second, or some more aggressive, more abrupt attacks. And we tested it. We used it to test all the telecom timing receivers we had in our labs at the time. So that's going back to the first GPS-based SSU type receivers all the way through to some of the more modern, and again, this is back in 2013, so this is 10 years ago. Some of the more modern NTP time servers and PTP reference clocks that had GPS references built in. We've tested them all, did a report on that, and not surprisingly, everything failed. When I say everything failed, I mean everything was spoofable, which is not surprising really, because all the receivers up until that point, so 2013, were probably based on late 90s, early 2000s technology, and obviously around that time, it wasn't considered a risk factor, or it wasn't considered in the design of those GPS modules that the GPS signal might be maliciously spoofed. Come forward a few years, so ITSF in Edinburgh, some of our colleagues from Spirent and Calnex presented some detailed lab tests that they performed on, again, similar situation, but they were using 2 Spirent simulators, a few more sophisticated scenarios in terms of trying to represent actual spoofing attacks that you might see with a signal from the live sky and then a signal from a spoofer. But again, they came to more or less the same conclusion in that all the receivers they tested were able to be spoofed. And then moving again further into the less distant past, 2020, 2021, Chronos took part in some research work that was funded by the European Space Agency as part of their NAVIST program. And this was looking at alternative sources of time for PNT systems. So what we built here was a test bed that could use different spoofing scenarios, basically to effect. We constructed what we considered to be in the top right-hand corner, those 3 boxes, the GNSS firewall, the GNSS receiver, and the alternate frequency and phase source. We'd constructed what we considered to be a smart receiver, where the GNSS firewall is a box that does much more low-level detailed analysis of the GPS radio signal. Some of the most basic spoofers leave lots of the data in the actual navigation messages that the satellites broadcast. The simple spoofers leave lots of that data set to default values. So one of the things the GNSS firewall is, it looks for things like default values, maybe the wrong case being used in some of the messages. We'll also look for large changes in power of the received radio signals, large changes in position or time that are also maybe indications that it isn't a live sky signal. And then this particular version, this particular box is in this testing, we used the Blue Sky box from Microchip. Has 2 separate outputs. One of the output is a pass-through from the live sky signal. So if everything is okay with the live sky signal, then that gets passed through to a GNSS receiver. If the firewall thinks that that signal is being spoofed or interfered with, it will disconnect that signal. So the GNSS receiver that it's connected to will then go into holdover, which might be how you want your systems to behave. The other output from this particular firewall is, again, another simulated GPS output. So the firewall itself contains a GPS signal simulator. The time base for that signal simulator can be based on the live sky, or if the live sky signal is interfered with, then it can fall back to using an internal miniaturized atomic clock, or you can feed it with 10 megahertz and 1 PPS clock signals from a co-located cesium, maybe, or other alternate clock source. And as part of this research, we were looking at using low frequency radio signals to provide the sync reference, so either ELORAN or the BBC Radio 4 transmitter that's in the UK is traceable back to cesium clocks. There's a time code signal on it, so we can as well get time and phase from it, or using 5G or LoRaWAN, for example, sort of local radio signals to get sync into. So that was the point of this particular piece of research, but again, use some very, very sophisticated spoofing scenarios. We had one simulator from Spirent and two from a French company called Syntony, and they'd written for us some very sophisticated spoofing scenarios that you might expect to see. We connected all the radio signals together through a combiner. We had an interference source, just a noise jammer, and we had an aerial, an antenna, a live sky signal that we could mix in as well. And of course, it was looking at proving just how we could use alternate time sources effectively to keep this critical infrastructure going that might be using older, less intelligent GNSS receivers. Back in 2019, I asked myself the question, could I build a spoofer that was small, portable, battery powered? I mean, we know that we were using these lab-based, these big expensive GPS signal generators, but turns out that the embedded engineering team at Chronos that were working on some of the devices that we build, they were using an open source SDR, this Lime SDR, software-defined radio, as a basic GPS simulator to test leap second scenarios. So whenever there's a leap second, things usually go a little bit wrong. So they were using a Linux PC with this SDR and a direct connection to the unit under test to be able to repeatedly test these leap second scenarios. So I asked myself the question, would it be possible to build a scaled down version of this with a battery, something like a Raspberry Pi and the Lime SDR or the Lime SDR Mini? And of course, the answer is yes. Whatever idea you think of, somebody's already done it on the internet. Turns out there are lots of people that have done GPS signal simulation, lots of academics. There was a study in Manhattan where they used a hack RF1 software-defined radio and a Raspberry Pi, put the whole thing in a lunchbox, and actually managed to fool sat-nav. In their test scenario, they wanted to make people take a wrong turn, make people make a wrong turn in Manhattan to prove that GPS could be spoofed in terms of position and navigation. So there's code on GitHub you can download. There are tutorials on how to do it. You literally copy and paste the commands onto the command line of the Raspberry Pi. You can then pull the code from GitHub, compile it. You get a couple of configuration files that you can either get from NASA or the GPS website via FTP if you want. And this is the spoofer that I built. I initially chose a Raspberry Pi 4B because I wanted to power the Lime SDR from the USB 3 sockets, but it turns out the USB 3 sockets are current limited on the Pi anyway, so I had to use a separate battery for the Raspberry Pi. The Raspberry Pi was just powered from a simple, a single.
Okay, see you later. Okay, bye, love you.
I'm getting some noise with somebody not on mute. I can hear some.
Yeah, I'm muting it. Sorry, go ahead.
Okay, I can't share my screen. I don't think I'm a presenter anymore.
Oh, okay.
I can't share my screen.
There you go.
Okay, thank you. Yes. Yeah, we're back. Thank you.
Yeah.
So it was powered, just a standard mobile phone, power bank, powered the Pi. I had a couple of laptop lithium ion cells that I'd reclaimed that I made into an 8.4 volt battery for the Lime SDR itself. But I also added another GNSS receiver because I wanted to synchronize the whole thing to UTC or to Live Sky. So I connected this all together and was looking at how to test it. The cases I'd seen where they built it, they put it in a lunchbox, so I scrunched it all up and tried to fit it into a plastic box. But around about this time, my youngest daughter was moving up from junior school to senior school in the UK. I think that's maybe high school in the States. So she was having a big clear out of all her old baby toys and soft toys and things, and she threw away, she didn't want this metal lunchbox. So I put the spoofer in this metal lunchbox. And I put some shell script on it and had a web front end so I could turn on the hotspot on my phone. The Pi would connect. I could connect through the web GUI, set the parameters of the spoofing, and generate GPS signals. But of course, the question everybody asks is, does it actually work? And the answer was yes. It did. We managed to, with this very simple setup, make time jump backwards, so start spoofing in the past. Lots of receivers crashed. Some of them required a power reset. I guess their firmware software wasn't designed to encounter backwards jumps in time. Again, steer the time forwards and then stop, which is more or less the same thing. Different receivers handled it in different ways. And again, steering time backwards and then stopping, you get a jump forward. So lots of the receivers were confused by this. They all handled it in different ways. And I guess that's part of the work that's going on at the moment in the resilience project in the IEEE, looking at defining how receivers respond to this. Some of our colleagues in the UK, the company that actually run the TV and the radio transmitters, they did some testing with a Spirent simulator and managed to spoof time 20 years in the past or the future, which is bigger than the GPS week number. So effectively the GPS week number rolls over. It's a 10-bit number, so it's 1,024 weeks, which is 19 point something years. And they actually bricked a receiver doing this, so the receiver wouldn't then restart. It had to go back to the manufacturer to be reflashed. So it is an issue, and it's becoming more prevalent. I think we're becoming more aware of it. It's not only spoofing with low-cost spoofers, but also jamming. These three jammers in the bottom left of the screen are from personal privacy jammers right through on the right-hand side. The big jammer with all the antennas on it was recovered from an organized crime group that were stealing high-value vehicles and jamming not just GPS, but all the mobile cellular frequencies, Bluetooth, Wi-Fi, and some specific frequencies that some dedicated vehicle trackers were using as well. So it's not just obviously attacks on the radio interface, traditional cybersecurity, as you might call it. Lots of these systems are network managed, so they have network interfaces, so they can fall into the category of the standard cybersecurity attack vectors. And also we're hearing more and more about space-based attacks where nation states are deliberately destroying old satellites and creating fields of debris that are close to where the GNSS constellations are, or even have dedicated systems that could attack directly those satellites. So there are things we have to consider. And Dana Goward on LinkedIn posted a couple of weeks ago that the cybersecurity mindset seems to be the way forward in getting the right engagement when talking about resilience for time, rather than just talking about it in terms of critical national infrastructure, maybe electronic warfare. Cybersecurity seems to grab everybody's attention and will dedicate resource in terms of time and money to addressing some of these problems. A case study here, one of our partners that we were working with, one of the power industry, the power utility, one of the distributors who build and operate one of the distribution networks, asked us to do some audit work in their digital substation. So the IEC 61850 digital substation standard talks about using digital techniques and sampled values to monitor current and voltage. And it calls for PTP to be used over these Ethernet type networks. And they were worried about what they were called this GNSS antenna proliferation. So the bottom left photograph here on the screen shows 21 separate GNSS antennas. This is a digital substation site built by a particular system integrator. The same network, the same distributor also has another site, the photograph on the right, built by a different system integrator. And this site had 11 GNSS antennas. And obviously, in terms of that cybersecurity mindset, the attack surface expands. The attack vector is still the same, but now the surface is 21 times as large because we've got 21 different antennas to go after. And this happens partly because in the digital substation, a particular function is installed in sort of a copy and paste sort of a way, where you might have a whole rack of equipment that performs a particular function, like fault location on some electrical transmission systems, and it needs a reference clock, so it has its own GNSS antenna. But it's also partly because of incompatibility and interoperation issues between different PTP profiles. So of the 3 power industry PTP profiles at the moment, the original 2011 IEEE version, the later IEC so-called power utility profile, or the revision of the original IEEE, the 2017 version, in some cases, this distributor told us that not all of the equipment was compatible with all of those profiles. So in some cases, they had to drop back to use SNTP. So they were effectively using NTP. So that meant they needed a separate clock that was an NTP reference. And it's, I think, part of the way that these power industry networks are built is that they're built in this rack style, very like Lego brick style of adding things, and then ending up with these lots and lots of different antennas, which just seems crazy. So in terms of resilient timing, best practice is own your own timescale, trust no one, and test everything. What I mean by that is own your own timescale, bring some resources in-house, so don't just rely on outside time signals, whether that means cesium and GNSS clocks or other dedicated timing systems. Trust no one, be very careful in accepting signals from outside sources. At least make sure that you're permanently monitoring those signals so that you can spot if the time from somebody else differs drastically from an ensemble of time from other sources. And test everything, test and monitor permanently to make sure that you're on top. And these philosophies are carried forward in some of the ITU architectures that I'll be talking about in these latter slides. In terms of the power industry case study that we had, we proposed to them using a GNSS firewall, so cut down the number of antennas per substation to maybe 2 or maybe 4. So you still have some redundancy, but you don't have that ridiculous state of affairs with 21 antennas. Use the firewall and then take either its validated or its hardened output. So it's either the pass-through sky signal or the simulated GPS signal. Using the appropriate GNSS signal splitters, we can then fan those out to as many receivers as are in the substation, and either use the miniaturized atomic clock for holdover in the GNSS firewall, or use the Telecom network to supply traceable time, UTC traceable time from somewhere else outside of the local area, so that you can then carry on providing a GPS-like signal to all the timing clocks that might be inside that substation. So now, the last section, the evolution of these ITU reference clocks. Talked a little bit before about the original PRC specification, G811, going all the way back to 1976. The so-called Orange Book, CCITT standard. And then it was a long time before, relatively, in 2012, when the PRTC was defined by the ITU in 8272. So the first time then that rather than the clock just having a frequency output, now has a time and phase output as well. Both of those specifications were then enhanced in 2016 and 2017 with the enhanced primary reference time clock, going from using single band GNSS to multi-band GNSS. So part of the unknown, part of the error in the navigation solution and the time solution is due to errors in estimating what's known as the pseudo range. So the distance the receiver estimates the satellite is away from it. In a single band receiver, there are variable delays through the ionosphere that we can't accurately predict. In a dual band receiver, different radio frequencies get delayed differently through that layer. So that receiver can then make an estimate of the extra delay through the ionosphere and get a much more accurate time solution. And the enhanced PRC was just a frequency clock, but with an order of magnitude better frequency accuracy over its lifetime, apart in 10 to the 12 rather than 10 to the 11. And then the latest concept within the ITU is this so-called coherent network primary reference time clock. So it's taking the clock combiner idea from the enhanced primary reference time clock, where you combine a local cesium and GNSS. And in the coherent network primary reference time clock, we're also able to take other clock signals into that clock combiner algorithm. So they could be direct feeds from a national lab. So you could have, in the UK, we'd have UTC NPL or UTC NIST or UTC USNO in North America, or maybe other PRTC clocks in the network. And it's this idea then of creating these clock combiners in different parts of the network to add resilience so that we can then move away from complete reliance on these GNSS signals that we know are spoofable. The ITU standard that defines the PRTC has this block diagram in it, and it shows in our old PRC we had the bottom two right-hand blocks, the frequency interface and the local frequency clock. We've now added the time recovery block, the local timescale. We've added these two logical outputs, so the time interface and the phase interface outputs. They're logically separate, but they physically might be on the same connector or the same signal, might be providing both. And we've got an external frequency input reference as well, which is optional. But the PRTC in its original form was supposedly giving us better than 100 nanoseconds error to UTC. The enhanced PRTC was then giving us better than 30 nanoseconds error to UTC, and also using this clock combiner technique where we effectively, over a period of weeks, work out using the GNSS. We use that as a long-term stable UTC traceable clock, and we work out what that very small frequency offset is of the local cesium, so that when the GNSS signal goes away, we can account for that. And the specification for the PRTC, for the ePRTC, is better than 100 nanoseconds of error to UTC for 14 days after losing that GNSS signal. And the sort of state of the art at the moment is this coherent network PC. Coherent network PRTC. It's defined in an appendix of G8275, so it doesn't really form part of the official standards definition, but the ITU is still working on finalizing this, and it will be defined in a standard shortly. But you can see the functional blocks are more or less the same, but we're just taking the clock combiner function, rather than just being restricted to a GNSS signal and a local cesium clock, is now able to take many more clock inputs. And in the top right of this slide, we have these two different proposed network architectures these are just copied and pasted from the ITU standards, where we have this meshed central core architecture with 6 nodes, or we have this regional architecture with 3 nodes connected. The idea is that this now can give us complete resilience in the network. But as I say, this isn't standardized just yet. So in terms, getting back to the title of the presentation, the network is the clock. This VPRTC. So the V isn't standardized. It doesn't appear in any of the ITU standard. It's really a marketing term. But the idea is that we have our ePRTC, so on the west side on the left and the east side on the right. We've also incorporated some of those GNSS firewall philosophies into our receiver, so it's now no longer a separate unit. It's part of the ePRTC function. So we're looking much more in depth at the actual structure of the GPS signal, looking for default values and wrong values in some of the actual navigation messages, so we can spot simulated or spoofed signals. And we are using these Class D high performance PTP boundary clocks connected directly over DWDM networks. So we're connecting them, so they're physically connected over dedicated wavelengths. So this is a dedicated physical link. So in terms of the PTP packets here, there's no switching, routing, there's no PTP, there's no packet delay variation. They're effectively directly connected using a couple of different techniques that are available in DWDM networks. And if we can do that, we build these sort of horseshoe-shaped network architectures, and anywhere we can connect to these high-performance boundary clocks, these high-performance boundary clocks add a few nanoseconds of error through each hop. So we're getting, tens of nanoseconds of error to our PRTC clocks, which is where the virtual, comes from. You connect anywhere on this DWDM network, and it's almost like you're connecting directly to the PRTC, hence this sort of marketing term for the vPRTC. This is the Telecom example. So this is vPRTC architecture supporting 5G. We've got the remote radio heads, we've got the DUs and the CUs, the 5G network architecture that's all timed back to the network, synchronized to our virtual PRTC architecture. In the power industry, we're working with operators in the UK that are deploying this architecture right now. They're deploying the PRTCs in their DWDM networks. They're upgrading to have these high performance boundary clocks in the network, so that in our digital substation that we have now, we have our duplicated time servers. So we have 2 local GNSS antennas. We also have fallback, if we want it to be fallback, if we want to use the GNSS clock as a primary source, or you could use the vPRTC as a primary and use the local GNSS as a backup. But it's the same sort of idea. Wherever the DWDM network extends to, we can get PRTC quality timing there. And one of the distribution operators that we were working with recently, they're looking at extending this to their analog assets. So not maybe going full digital substation, but they're building effectively a telecom timing rack that has the DWDM equipment in it, a high performance boundary clock, and a time server as well. So they can then drop that rack into locations where they have analog assets and build and integrate those into their digital networks. And the data center example, this is the classic European Frankfurt, London, Amsterdam, Paris data centers. Again, we've got 2 PRTCs, we've got west and east, we've got 2 this time horseshoe networks, one to the southern half of the ring, one to the northern half of the ring. And again, we can use these PRTC clocks to get accurate UTC traceable time into data centers that can withstand GNSS outage. So if the GNSS signal is interfered with locally, or if there's a regional or a global event, then the PRTCs will fall back to using their slightly adjusted cesium frequency to give you much better than 100 nanoseconds of error over the first 14 days. So we're not quite at the full coherent network PRTC deployment yet, but this is what's available now from the equipment vendors in terms of the building blocks that we can use, the PRTCs and the high performance boundary clocks. We can build networks that support these applications to those levels. So a very particular example for the UK, NPL is the National Physical Laboratory. It's the National Metrology Lab in the UK. They provide the UK's contribution into UTC. And for a few years now, they've been working on this so-called National Timing Center program. They're building a geographically distributed network around the UK. So they're installing atomic clocks around the UK, networking them together in the sort of coherent network PRTC style. They're working with telecom operators, and the idea is that then they will produce a resilient timescale for the UK that is or can be independent of GNSS. And they provide points of presence where at certain data centers they can offer connectivity. So industry, commerce, academia can all connect into this resilient national time base. And they're also, as part of the program as well, they're promoting training to upskill around time and frequency knowledge, and they're also providing grants for innovation. If this network is fully available, what sort of innovative services can we build on top of this network? So that's a very specific UK example of the network being the clock. So to summarize the last two slides here, I think obviously these telecom networks, we can build them now to provide your own time, whatever time scale you want to call it. It can belong to you. It can be under your control with these sort of building blocks, these ePRTC clocks networked over DWDM with high performance boundary clocks can give us these levels, tens of nanoseconds, less than 100 nanoseconds Verita UTC, and all the applications that they can support. Anywhere that you have optical network access, you can have access to your own timescale. And obviously, as I've said, you can have that primary reference and use GNSS only as a backup, or it can be a backup if GNSS is denied regionally or nationally. So the network is the clock. Is the network the clock? Obviously, I think now much more focus on resilience. Increasingly, it means security, availability, and autonomy for time. These network architectures, the vPRTC, can supply resilient time everywhere. The coherent network PRTC is bringing the sort of national timescale performance into telecom networks. And it's always worth remembering there is a large installed base of what I would call dumb timing receivers that will follow any signal that looks like a GPS or a Galileo or a GLONASS signal. So they don't need to be forgotten. You need to remember those. So there we go. That's the end of my talk. Thank you for listening. I hope it's been useful and or interesting for you. My contact details are all there. Do we have any questions?
Thank you, Chris. This was a great presentation. Let's open the floor for questions. Any questions? Maybe I can start with one. So how do you, in general, strike a balance between having the flexibility to accommodate, let's say, adjusts that they're legit from, let's say, adjusts that they come from a spoofing event in general?
In terms of GNSS signals?
That's right.
Well, one of the things I didn't mention in the presentation is obviously that there's been lots of focus on resilient timing for a good number of years. The satellite constellations themselves are starting to broadcast authentication signals, and there are other. We've seen presentations at some of the conferences. There are other systems being used to ensure authentication. There are partnerships between particular operators and equipment vendors. But in terms of GPS, they were trialing an authentication signal called Chimera. Galileo has this OSNMA signal, which again is authenticated. So it should be a lot easier in the future to work out if you are seeing an authentic signal from the live sky. But yeah, I think we'll see more partnerships between maybe things like the National Timing Centre in the UK, where that will form part of the overall authentication for timing, and it will just be a case of maybe just comparing the clock. You've got your trusted source from NPL, for example, and if your satellite clock starts to drift off from that, then you distrust it. So
yeah. And so let's see, I think we have a question. Yeah. So I mean, in general, do you see there will be still a future, let's say, I don't know, let's say 10, 20 years we go forward, let's say to rely still on timing from satellites, or like GNSS will be simply just for, let's say, positioning?
I don't know. It's a difficult question to look in the future, but I guess in one respect, if we do end up in a sort of hyper-connected world where we have much more local radio networks, like some of the LoRaWAN, some of the metro networks, Wi-Fi everywhere, 5 or 6G everywhere, then maybe we won't rely purely on GPS as much. I think lots of work and lots of research at the moment is being done on signals of opportunity. So using things like TV, using DVB terrestrial TV transmissions and other things. And I've also seen some really interesting presentations at conferences from optical navigation, where just looking at landmarks and then all the thing with inertial navigation. So in the future, maybe no, we won't be anywhere near as reliant on GPS for time, because we'll have all these other sensors, other signals, and other technologies. You know, we might even have miniaturized atomic clocks in our iPhones. Who knows?
Yeah, no, definitely. So, maybe another question as a follow-up. Do you see, let's say, power becoming source for timing?
Power is difficult because at the moment, in terms of the frequency of the grid, that's difficult because at the moment we're still in a transition point between the old way of generating, which was the huge spinning machines with lots of inertia, and trying to balance supply and demand. They would speed up or slow down. So the frequency, it's quite a wide range of change in frequency. It's never in the middle. It's either, you know, it's more often too fast or too slow than it is accurate in the middle. But I guess if we move to a world eventually where there's lots more micro generation and it's either DC, you know, solar photovoltaic or wind farms or DC to AC conversion, then, you know, maybe in the future it will be good enough, because, you know, power is just about everywhere anyway. So
Exactly.
yeah, interesting.
Yeah, like I see also all this effort in power for bringing precise time for like smart grids and so on. Well, might as well use it for the SRCs, and now you have like the generation, the 60 hertz or 50 hertz.
Yeah, there's
More
lots.
precise. Any question? Anyone else? All right. Hearing none, then we'll adjourn.
Thank you very
Chris,
much.
thank you again for this presentation, and looking forward to seeing everyone in 2 weeks, which will be a call about security. So great. See everyone.
Thank you. Thanks. Bye.
Bye.